Everybody, happy Easter. This is Lucas Wilkerson, the math coach here at FGCU, and we're going to be working through 4.4 and 4.5. So looking at question number 1, it says solve the equation by expressing each side as a power of the same base and the equating exponents. Basically a fancy way to say solve for x. So let's see what we got here. 3 raised to the 6 minus 3x equals 1 over 27. So we're going to need to get that x out of the exponent. I see that we have a 1 over 27, which can be expressed as 3 raised to the negative third. And the reason that's useful is then we can just cancel out the 3's on both sides. We're left with 6 minus 3x equals negative 3. Then you change that. You just add 6 to both sides, or subtract 6, my bad. And you're left with x equals 3. Number 3, it says solve the exponential equation, express the solution set in terms of natural logs. So doing the same thing, solving for x, but we need natural logs in our final answer. So let's get that 7 out of the exponent by taking the natural log of both sides. And that'll bring the 7x over here. Then let's see, what do I want to do next? Let's divide both sides by 7 ln 2. This is actually not supposed to be 2x, just supposed to be 2. And what that will leave us with is x, so just x on our left side is our goal. And I did not write this well. This was supposed to be ln 4.9. So we took the ln of both sides, the natural log, and then we brought this 7x down. And now we're going to divide by 7 ln 2 to get x by itself. Your final answer looked like that. Number 6, it says solve the logarithmic equation. Be sure to reject any value that's not in the domain. Give an exact answer. So again, we're going to solve for x, but when we get to the end, we need to check if it works for the domain. When we check for the domain of a logarithm, we cannot have any negatives inside the parentheses of the logarithm. So I'll show that at the end. Let's see, we have log 4x plus 2 plus log 4x minus 4 equals 2. We know the rules of logarithms says we can change these to multiplication, which would be very helpful. And we can change this to 4 squared equals x plus 2, x minus 4. This is just 16 in this. If you go through and do the FOIL work, you get this. We can subtract 16 from both sides and simplify. Now we can refactor this. We would ask what two numbers multiply to negative 24 and add to negative 2. If you do a little guessing and testing, you'll see x minus 6 and x plus 4, which means x is 6, x is negative 4 for our answer. And the way you want to test these for the domain is you want to go back and plug them into the original equation. So if we plug in 6, we're not going to get negatives in either of our logs, so neither of these pieces turn negative. But if you take negative 4, this x plus 2 and this x minus 4 will be negative. So we're going to reject, oh my bad, we're going to reject the minus 4 and just say 6 is our answer. All right, I'm going to do something similar for number 8. This time we have subtraction. Yeah, we have subtraction. So it's going to be division by the logarithm properties. So this turns into log 3, x plus 4, x minus 5 equals 2, which can be changed to 3 squared equals x plus 4 over x minus 5. Then we want to multiply both sides by x minus 5. Cancels that out. Makes our left-hand side 9x minus 45. Makes our right-hand side x plus 4. Shuffle the terms around. Get 8x equals 49, which if you divide both sides by 8, gives us x equals that 49 over 8. On to the next section, we have some good old fun word problems. Okay, looking at number 2, this is the value of a particular investment follows a pattern of exponential growth in the year 2000. You invested money in a money market account. The value of your investment T years after 2000 is given by the exponential growth model, A equals all that. When will this account be worth $11,405? So we're given the number that we're looking for, like the total amount, but we're not given the T. So it looks like we're going to solve for T here. So using this equation and this amount, we'll solve for T. Perfect. Let's try and get T by itself a little bit more. We'll divide both sides. That cancels out. And then we'll take the natural log of both sides. What's important to remember is ln is actually equal to log base e. And if you ever have a log like this, let's say log 2, it's raised to 2x, this part will cancel out in the log, and you'd be left with just x. So in our case, since we have log e, this cancels out. Since that cancels out, we're left with ln 11405 7200 equals 0.46t. Divide both sides by just 0.46. And if you plug that mess in your calculator, you'll get about 10 for t. Number 4 says the half-life of silicon 32 is 710 years. If 50 grams is present now, how much will be present in 100 years? Round your answer to 3 decimal places. Here we need to remember the half-life formula, which is going to be A equals A sub 0 EKT. For the first piece, we're given the 710 years, and since we're taking the half-life, we know it's just going to be half, so 0.5, so we can plug this in as 0.5 equals E, there's a 1 there, A sub 0 is just 1, because we're just using 1 year. It's going to be K 710, that's the 710 they gave us. We can take the ln of both sides. And when we have ln e, we remember that it cancels out. Divide both sides by 710. And we see that k is about negative 0.000976. Bringing us to the second part. We're going to use the same equation, but with new information. We can plug in our t that we found. And now we can evaluate how much will be present after 100 years. So we're going to have A equal to 50 because of 50 grams, E then 100 times this fun number. If you plug that all into your calculator, you'd get A equals 45.349, roughly. Now for the last problem, number 6. It says solve the problem. The logistic growth function, ft equals all that, describes the population of a species of butterfly 2 months after they are introduced to a non-threatening habitat. How many butterflies were initially introduced to the habitat? So to ask this, this would just be plugging in 0 for time. That would give us how many butterflies are there initially after no time has passed. Plug all this into your calculator and you'll see there are about 70 butterflies. Next it asks us, what is the limiting size of the butterfly population? When it asks for limiting size, you're just going to look at the numerator or equation. So in that case, it would be 680, not going to exceed 680. And then for C, how many butterflies are expected in the habitat after 13 months? So like part A, instead of plugging in 0, we're just going to plug in 13. Plug that in and solve, and you get about 540.